When you begin working in fluid mechanics, it's useful to have a model in mind for what the fluid is, how it behaves, essentially how to think of a fluid. It's really not that complicated. Let's take a look at it together. We may start with the question, what is a fluid really? And you may want to answer this question by thinking, well, a fluid is matter and matter is made of molecules, so ultimately a fluid is made of molecules. But in fluid mechanics, it's not quite true, and we're going to see why. Imagine that you want to measure a property here in the room. Let's say you want to measure pressure or temperature or velocity. And you start off by taking the average value of, say, temperature for the whole room. And now you become more and more focused on a smaller and smaller volume so that you are becoming more and more precise. What happens to your measurement? You start with the average value of, say, temperature, and that goes down or up as you reduce your volume towards a fixed value. And that fixed value is the value of, say, pressure at that point in space. What happens now if you become too precise? Your volume becomes too small. Your measurements start to look pretty odd. What happens is that the values of your measurement will start to oscillate wildly. And this is because as your considered volume becomes smaller and smaller and smaller, you start having the effect where the head of your sensor, super precise sensor, sits in vacuum all the time until a molecule comes and hits it. And as the molecule hits it, the measurement value bumps up, shoots up, and you measure nothing again. In fluid mechanics, we choose to split this diagram into two parts. The part below the red line is called the microscopic scale, and that's the part where you start to feel the effects of molecules. And we choose to ignore that part, and we stay in what we call the macroscopic scale here, where you measure only the properties of the fluid, of the molecules in aggregate. Now this all sounds a bit vague, so let's take a concrete example to see what numbers we can put on this. Let's say it's a nice calm summer day. You're in the mountains and you're looking at a white water river flow. What are the scales that we are considering here? What is the distance between molecules and how small is really the flow structure? The average distance between molecules in a fluid is called the mean free path. In water, it's about 100 picometers, which is 10 to the power minus 10 meters. In air, above the water, in our case, it's a lot more, 60 nanometers, which is about 10 to the power minus 7 meters. Okay, these are very small numbers. What about on the other side of the big red line? Well, the smallest flow structures in a turbulent mountain river flow are about 1/10 of a millimeter in size. And above that river, in the atmosphere, on a calm day, there's no wind, the smallest structures you're going to find about 1/2 millimeter in size. These are very small numbers, micrometers, nanometers, picometers. So what happens if you put them all together on the same graph? Well, what happens is that the mean free path is barely noticeable on the diagram where you also plot the smallest flow structures that you will encounter in fluid mechanics. To read those four numbers together, you need a different scale, a logarithmic scale. Let's take a look. Looks like this. This is a very tricky scale to read, especially the first few times where you're working with it. Pay attention that every one number in here is 10 times smaller than the number after it. So every time you multiply the distance by 10. Right? And I think you spend a little time reading this diagram and you will find that the distance between molecules is about still 10,000 times smaller than the smallest flow structure you're going to encounter in fluid mechanics. So in fluid mechanics, the smallest unit of fluid that we are considering is still a group of billions of molecules. We call this unit a fluid particle. The size of a fluid particle depends on the flow, but a good order of magnitude to keep in your mind is about 1 millimeter cube, or a big grain of sand. To us, in fluid mechanics, the fluid is a continuum. There's no gap inside the fluid. Yes, we can differentiate all the variables as we like. Yes, and to us, really, the fluid is made of fluid particles and not of molecules. To the fluid dynamicist, air is not made of molecules, it's made of air. Now you may be thinking, this sounds like some kind of a lie we're telling ourselves to make our lives easier, right? And you may want to start with the fundamentals, with the molecules, in order to describe the fluid flow. Well, if that is the case, I've got something for you. Something is a jar of water. There's about 1 liter of water in here. How many molecules are we talking about? Well, the 1 liter of water is about 3 times 10 to the power 25 molecules. All right. The water may be standing still, it's in the jar, it's not moving, but the molecules inside it, they are moving, and they are moving at 5,000 kilometers per hour, approximately. That's about 3,000 miles per hour. And I think the scientific term to describe this is, because if you want to describe this jar of water, you want to calculate this jar of water, you need to solve 3 times 10 to the power 25 equations. And each of these equations describes the position of one molecule. And since the position of each molecule depends on the position of all the other molecules and should keep bumping into one another, each of those equations has 3 times 10 to the power 25 unknowns, right? So you're very brave. You're courageous. You launch into this calculation, calculating all these millions of collisions every second. And then you take the average of all these movements to reconstruct the movement of the water. And what do you get? Well, you get 0 because the water is not moving, right? So I think you can see here that calculating the movement of fluids using the movement of molecules, it's not a feasible approach. There are consequences to this. And the way we think about fluid particles is very different than the way we think about molecules. Here's a wind tunnel from NASA, and smoke is being injected in the wind tunnel, and it flows around a model. So we see the movement of fluid particles here. I think it's pretty clear. You can see that the fluid particles are able to turn. They're able to turn upstream of an obstacle and then downstream of it again. The same thing is visible here in a very low-key fluid flow simulation. This is something you can run on a tablet. And the dots here represent positions of fluid particles. And you can see, I think, pretty well, the particles do not behave like molecules. Molecules would just fly in a straight line in vacuum until they hit something and then bounce off of it. But here the fluid particles are able to turn around objects and turn around themselves. So here are 4 ideas to conclude to describe the movement of fluid in your mind, how to think of a fluid. The first idea is that fluid particles constantly push and rub against their neighbors. By this I mean that molecules are always alone in vacuum, right until they come very close to another molecule and interact one with the other and then become alone again. Fluid particles, on the contrary, are always in contact and always pushing on their neighbors and always rubbing against them. The second idea I want to communicate is that particles always occupy all of the space available to them. Well, you may be thinking, well, second, I just saw a jar of water and it was pretty clear in this jar that the water did not occupy the whole of the jar. And I agree, but a fluid dynamicist would say there are actually 2 fluids in this jar. There's water and there's air. And if I were to pump out the air of this jar, you would see the water instantly start to boil, and at equilibrium would get liquid water and gaseous water on top. So particles always occupy all of the volume you make available to them. The third idea is that particles turn and strain. Particles are able to turn upstream and downstream of an object. They're very different from molecules, which just go in a straight line until they hit something. Yes? And while they move, they also strain, they change shape, they elongate, they squeeze, they expand. finally, the last idea I want to communicate is that all the movements of the particles are connected. By this I mean it would be tempting to do in fluid mechanics like we do in solid mechanics. That is, take a particle at the inlet of a flow and calculate the movement of that particle. So follow it along, calculate the dynamics of it, its trajectory. And once we're done, then start over with the next particle and then calculate the movement of that one. And then take the next one and so on and so forth. But that is not going to be a working approach, because the behavior of a particle, in particular its acceleration, is very strongly determined by the neighbors, the immediate neighbors of any particle at any moment. So the right way, and the way we do it in practice in fluid mechanics, is to calculate all of the particle movements all at once, simultaneously. Now I realize that these four ideas are expressed in a very qualitative way, but we'll see that there are some really strong physics fundamentals below that. And of course we'll learn to re-express those in a clearer and more mathematical way so that we can use them to calculate the movement of fluids, so using hand calculations or computer code, yes? And I really look forward to do this with you in the coming videos.
Hi, I am Olivier Klein and I'm recording a video course in fluid mechanics. If you find this video useful, check out the rest of them at learnfluidmechanics.com. I hope to see you there. Take care.